Here are the Chapter 2 notes. The law of conservation of mass says in a chemical reaction, mass is neither created or destroyed. The law of definite proportions says all samples of a given compound always have the same proportion of their elements. What that would mean for you is this. There we go. If you have water from any source, if you found water trapped in a rock, if you found water from your kitchen sink, it would all be the same, two H's combined with an L. The law of multiple proportions says when two elements form different compounds, the masses of the elements combine in a ratio of small whole numbers. Okay, what? Let's try H2O and H2O2. That's what that means. The ratios are small whole numbers. All right, here are the scientists and their contribution to modern atomic theory. And I will leave you to read these, and I believe you studied it in Chem 1. We're not going to test it very often or frequently. It is fodder for the test for this unit, so please read it over. All right, and here is something else that you also know, that an atom is the smallest part of an element that retains the chemical property of that element. It's composed in the nucleus of a proton and a neutron. The proton determines the atomic number and gives it the element's identity. What that means is you can only have carbon if there are 6 protons in the nucleus. If you have 5 protons in the nucleus, it's going to be boron. The number of neutrons also residing in the nucleus can change. It determines its mass number. Together, the proton and the neutron make up most of the mass of an element, therefore most of the mass of an element is found in the nucleus. In the electron cloud, you find the electrons. They have a very, very small mass compared to the proton and the neutron. Please know that these are atomic mass units, and we can often make a reference to their mass in grams. However, no one is able to take a proton, put it on a scale, and mass it. It is a relative number. Okay, since the number of neutrons can change, that brings us to an isotope. An isotope is an atom of the same element that have different numbers of neutrons. Isotope notation looks like this. Please note, this is not what is on the periodic table. This refers to one particular atom. The periodic table refers to the weighted average of all the atoms of that element. This would be the symbol of the atom. This would be the mass number. The mass number is the number of neutrons and the number of protons added together for that particular atom. This is the atomic number, and it is the number of protons. Okay, let's look at the difference between two isotopes. Here are two isotopes of carbon. Since they both have the same number of protons, they both are called carbon. Their mass number is different, which means that the number of neutrons is different. If their mass number is 12, and they have 6 protons, 12 minus 6 means this particular isotope of carbon has 6 neutrons, while this particular isotope of carbon has 14 minus 6, or 8 neutrons. Sorry. Right. On the periodic table, you will notice underneath the element symbol, there is a decimal. That's because it's the weighted average of all the known isotopes for that element. How do you find that? You find it this way. To find the average atomic mass, you take the percent abundance, how frequently it is found. Let's say we're talking about carbon. There are 3 isotopes of carbon. There's carbon 12, carbon 13, carbon 14. There are many more atoms that have 6 neutrons than there are those that have 7 neutrons or 8 neutrons. And so that is reflected in the percent abundance. The percent abundance for carbon 12 is far greater than that of carbon 13 or 14. So to find the average atomic mass, you take the percent abundance, multiply it by the isotope of all of the atoms, all of the known isotopes. So here we go. In chemistry, we like to get rid of the percent sign right away by dividing by 100, and we will do that in this case. And we will follow the direction, 0.25 times the mass number of our first isotope of chlorine, 37, plus 0.75 times our second known isotope will give us the average atomic mass. You should see from the percent abundances that there are far more atoms that have a mass number of 35 than there are that have a mass number of 37. Therefore, our average atomic mass should be closer to 35 than it is 37, and that is indeed the case. Okay, so here's the definition of percent abundance. You know that cations are positive because they lose an electron. So a lithium atom, which started out with 3 protons and 3 electrons, will lose one of its valence electrons and become a positive ion, while fluorine will gain an electron to become a negative ion. An oxidation number tells us the number of electrons that will be lost or gained to form the ion. The representative elements are a new terminology for you. The representative elements are those that stick up above the transition elements. We will practice our dimensional analysis and mole conversions. Remember that the mole is a terminology that helps us convert from particles to liters of gas. Please remember you can only use this term if you are at STP. STP is 1.0 atm, which is the atmospheric pressure that you would find pretty much around you, but the temperature is 0 degrees C, which is kind of uncomfortable. Standard temperature and pressure. Normal temperature is about 25 degrees C. Okay, so here are the conversion factors that take you where you need to go. Remember, molar mass are the number of grams of a certain of the atoms in a compound. Let's take this compound, for instance, and figure out its mass, molar mass. This is sodium sulfate. First thing I do is list the atoms, and I count them. There are 2 sodiums, 1 sulfur, and 4 oxygen. Multiply them times the mass of 1 atom found from the periodic table. I'm doing this without a calculator and without looking at the periodic table, so I'm kind of guesstimating on my molar masses. There we go. So sodium sulfate would have a molar mass of 142 grams for every 1 mole of sodium sulfate that's available. Okay, we are going to talk about mass spectrometry in another